Quantum mechanics is, without a doubt, the most successful theory in the history of science. The accuracy of its predictions is just stunning. But for 100 years, we've been stuck in this debate about what the equations are actually telling us. So today, we're going to explore a really different interpretation, not of the math, but of reality itself. And this quote, this just gets right to the heart of it, doesn't it? We have a tool that works perfectly every single time. But the moment we ask, okay, so what is the universe really like according to this tool? The consensus just evaporates. We know what happens, but we can't for the life of us agree on the story of how. So let's just pose a different kind of question. What if all this quantum weirdness, the stuff that seems so paradoxical, isn't a bug in our understanding? What if it's a feature? What if these puzzles are actually clues, pointing us directly to the fundamental logic of how our universe is constructed? All right, let's dive into what we mean by this quantum crisis. It's not a crisis of math or prediction. It's a crisis of explanation. We can calculate outcomes with near-perfect precision, but we can't seem to tell a coherent story about what's physically happening underneath it all. I mean, these are the big ones, right? The questions that keep physicists up at night. When does that cloud of possibilities, the wave function, suddenly become one definite thing? Is superposition a real state of being? Is the particle actually in multiple places at once? Or is that just a reflection of our ignorance? And where exactly is that line, the so-called Heisenberg cut, where the fuzzy quantum world gives way to our solid classical reality? No theory has a knockout answer for all of these. So, to tackle this, we're going to walk through a framework called normiali. It's a non-ontological reality model based on an experiential ontology and logic of inference, and it offers a really radical solution. What if the problem isn't our physics, but our most basic, unspoken assumption about what reality is? And here it is. This is the fundamental flip. The default setting for most of science is materialism, right? The idea that matter is the base reality and consciousness somehow bubbles up from complex arrangements of it. This framework inverts that completely. It says, no, consciousness is the fundamental ground of being, and the physical world, all of it, matter, energy, space-time, is a phenomenon appearing to and within consciousness. Think about it for a second. Right now, science is trying to explain the one thing we experience directly, our own awareness, by using something we only know through that awareness, the physical world. This framework says that's backwards. Consciousness isn't the mystery we need to solve. It's the given. It's the non-negotiable starting point, the very screen on which the movie of the universe is playing out. So if consciousness is fundamental, what does that make the physical world? Well, it becomes a kind of shared, persistent, interactive simulation. And look, before you say that sounds like science fiction, just think about it. We all have direct experience with consciousness rendering a complete, immersive reality from pure information. It happens every single night when we dream. This framework just suggests that what we call waking reality is a much more stable, coherent, and shared version of that same fundamental process. Okay, so let's get into the technical core of this. How does this shift in perspective actually help us with quantum mechanics? Well, if reality is a kind of rendered simulation, then the weird rules of quantum mechanics aren't describing weird physical objects anymore. They're revealing the underlying logic of the rendering engine itself. Let's start with the wave function. In this model, it's not some spooky physical wave rippling through space. Forget that. Think of it as the rendering engine's internal data file. It's the system's way of tracking all the possible states a system could be in, what Heisenberg called potentia, before it's forced to actually render one of them into our shared experience. And the famous Born rule? What's its job in this model? It's the conversion algorithm. When an interaction, a measurement, demands a definite outcome, the Born rule is the specific piece of code that takes the complex data from the wave function, squares the amplitudes, and converts them into the real-world probabilities that we observe. It's the process by which the simulation commits from a set of potentials to a single actualized state. And this is where the so-called wave function collapse stops being so mysterious. It isn't a physical process at all. It's the rendering engine, switching its logic based on the situation. If an experiment allows for multiple unobserved paths, the engine uses wave-like interference logic. But the second you set up the experiment to get which path information, you force it down a single path. The use case changes, so the engine switches to its classical particle-like rendering mode. It's a change in the software's logic, not a change in the hardware of reality. This also gives us a really elegant take on decoherence. It's not about a conscious person looking at something. It's about the system's own need for logical consistency. The moment information about a particle's path leaks into the environment, creating a potential record of that path, the system has to lock in a definite state. Why? To maintain narrative integrity. It has to make sure the universe's story doesn't have contradictions or plot holes down the line. And this just dissolves the whole paradox of delayed choice experiments. Think about it from a processing standpoint. Why would the simulation render a photon's entire journey across billions of light years? That's incredibly wasteful. Instead, it only renders the final outcome, the detection. Then, if an experiment is set up to measure some aspect of its past, the engine generates a consistent history. It backfills the story on demand. The past isn't being changed, it's being rendered for the first time, just in time to be consistent with the present. Now, a framework like this doesn't just pop up out of nowhere. And one of its real strengths, I think, is its ability to act as a home for and to synthesize some really powerful ideas from some of the greatest minds in physics. What's so compelling here is that this framework doesn't throw everything out. Instead, it acts like this unifying hub for all these profound but seemingly separate ideas. It takes Heisenberg's potentia and calls them rendering possibilities. It accommodates Penrose's non-computable consciousness by placing it outside the simulation. It even aligns with things like constructor theory. It provides a single, coherent narrative that connects these powerful insights. Let's just look at two of them a little closer. Let's start with a big one, Heisenberg himself. He was already thinking along these lines. He didn't see the quantum state as a concrete physical thing. For him, it was pure potential, a set of possibilities just waiting for a measurement to make one of them actual. The Normoyele framework just makes this concrete. It gives Heisenberg's abstract idea of potentia a specific home. It's the data held in the rendering engine's memory. And probability? That's not some mysterious property of the universe. It's literally a rule in the source code that governs how one of those potentials gets selected to become actual. Okay, now let's bring in Sir Roger Penrose. He's famous for arguing, based on Gödel's theorems, that human consciousness must be non-algorithmic, that what our minds do, especially in terms of understanding, is something no computer could ever replicate. And the framework's answer to this is just, well, it's incredibly elegant. Of course, consciousness isn't computable by the simulation. It's the player, not a character in the game. The rendered physical world runs on algorithms. Absolutely. But the conscious observer, the one experiencing it all, is external to that system. It's a sovereign participant. Okay, I know what a lot of you are probably thinking right about now. This is interesting, it's great philosophy, but is it science? Can you falsify it? This is the crucial objection, and the framework meets it head-on by essentially reframing the whole debate. Here's the core argument. Asking if a foundational model of reality is falsifiable is a category error. I mean, take materialism, the default assumption. Can you design an experiment to prove that only physical stuff exists? No, of course not. It's a starting axiom. It's an unfalsifiable metaphysical position. The Normoyele framework argues that it's simply proposing a different, equally unfalsifiable axiom, that consciousness is fundamental. At this bedrock level, they're on the exact same logical footing. So if we can't use falsifiability as the yardstick here, how do we compare these foundational views? Well, we have to use different criteria. First, scientific adequacy. The framework can't contradict any known experimental results, and this one doesn't. It's designed to accommodate all of them. And second, explanatory power. How well does it make sense of the data we have? Does it resolve the paradoxes? Does it give us a more coherent and intuitive picture? And that's where this framework really claims its strength. So in the end, the question isn't, is it provable or is it falsifiable? The question is this. Given that any starting point is an unfalsifiable axiom, which one offers us more explanatory power? Is it a universe of mindless matter that somehow, against all odds, coughs up conscious observers? Or is it a universe grounded in consciousness that renders a consistent, information-based reality that just happens to follow the rules that we've labeled quantum mechanics? That's the choice this framework puts on the table.